Hello everyone and welcome to Valiant Tech World. Today we're gonna talk about some of the metrics used to evaluate the performance in regression problems. The main objective in regression problems is to find a function that is able to fit the data. This means to have a function which outputs a prediction y given input data x, where y and x are respectively called the dependent and independent variable. Several machine learning methodologies can be used to find this function. The example provided is for a single dimension, but the concept is the same in case of data with more than one dimension. Given some points, the solution of a regression problem is a function close enough to the data. In case of different points, then a new function needs to be found, as you can see. From a mathematical perspective, the goal is to reduce the difference between prediction, which is the output of the selected methodology, and the observed data points. These differences are called residuals. And the task is to reduce these residuals as much as possible. And in the example, you can see that the main function is in green, and the residuals are the red lines between the observed points and the function. I would like to digress for a minute, and it is important to remember that in machine learning, typically the data are split into training and testing data. A function is found using the training data and then it is tested on the testing data. The reason behind this comes from the fact that given a number of points, it is typically possible to find a function complex enough to reduce the residual to zero and touch all the data points. But that does not necessarily mean that the main characteristics of the data are learned, but more than the method has memorized the points, and this is not what you want. So, by using a different set, then the selected function is tested on data never seen before, in order to check if it is able to capture the main characteristic of the data. Coming back to the main topic, the goal is to reduce the residuals. They are calculated as a difference between the actual value and the predicted value of the function that fits the data. The table shows an example of actual and predicted values, and the associated residuals, which can be positive or negative, given that the function can underestimate or overestimate the actual values. The idea behind a metric is to have a number which summarizes the performance of the selected function. A possible metric is the mean absolute error. This metric sums the absolute values of the residuals, and this sum is divided by the number of residuals to get an average. It is worth noticing that the absolute value is used because we want to sum the magnitudes of all the residuals. If you leave negatives and positive residuals, they cancel out, giving the false impression that the error is small. Another metric typically used is called the root mean squared error. Here, instead of using the absolute value of the residuals, the values are squared, so also in this case they are all going to be positive values. Then the square root is used on the mean of these squared residuals in order to have the same units of the variable of interest. The main difference with the mean absolute error is that by squaring the values, the errors of the outliers increase, and this metric gives a high weight to large errors. So outliers, which are points with residuals typically much larger than the rest of the points, can influence more this metric value. We can show this with an example. Here we increase the first point from 4 to 4.1 and increase the last point from 2 to 2.1. Given that the first point was underestimated and the last point was overestimated, we essentially increased the distance from the prediction by 0.1 in the first case and reduced it by the same amount in the second case. As a result, given that the mean absolute error treats all the values equally, you can see that the new value remains the same, 0.5. On the other hand, previously the square residuals for the first and last point were respectively 0.04 and 0.16 for a total of 0.2. You can see that the increment of the first point is smaller than the decrement of the second point, and the total sum is now 0.18, which is smaller than 0.2. and for this reason the final value of the root mean squared error is smaller. In this other example, you can see the opposite scenario. The first point is decreased from 4 to 3.9, while the third point is increased from 3.7 to 3.8. The mean absolute error still has the same value, but for the root mean squared error, by further increasing the distance of the outlier, the sum of the first and third squared residuals goes from 0.68 to 0.82, and this results in an increased root mean squared error. In case outliers need to be reduced and taken into account more than the rest of the points, root mean squared error is typically a better choice. So, three metrics commonly used are the mean absolute error, the root mean square error, and then there is also the mean square error, which is like the root mean square error, but it does not calculate the square root. In this case, the units are squared, so they cannot be directly compared to the variable of interest, and there is not a direct interpretation of the result. However, in case the metric is used just to compare the performance of two functions, you might be simply interested in which one has the smallest value, and instead of using the root mean square error, you can simply use the mean square error and avoid to calculate the square root. All these metrics range from 0 to infinity, where 0 is the best value, which means that all the residuals have value 0. Software packages already include all these metrics, and you can select the one more suitable for your problem. The last metric that I want to describe is R-squared. This is mainly used in linear regression problems where there is a linear relationship between the input and the output. This metric quantifies the amount of variance of the dependent variable which can be predicted by the independent variable. To calculate the metric, we need to first calculate the total sum of squares. This is the sum of the squared differences between the points and the mean of all the points. In the example, you can see that the total sum of squares is the sum of all the yellow squares. Then, the second step is to calculate the residual sum of squares, which is similar to the mean squared error, but without calculating the mean. These are the squared errors of the functions that we believe is a good fit for the data. In the example, you can see that the residual sum of squares is the sum of all the red squares. And the third and final step is to calculate R-squared, which is 1 minus the ratio between the residual sum squares and the total sum of squares. This metric typically goes from 0 to 1. If the function is a perfect match for the points, the residual sum of squares is 0, and the R-squared is 1, which is the best value. On the other hand, if the selected function is not able to provide better result than the horizontal line, which is simply the mean of all the data, then the ratio is close to 1, and the R-squared is 0. In particular cases, the function selected is very bad, and the sum of all residuals is greater than the mean of the data, and this means that the ratio is also greater than 1, and R-squared becomes negative. And this type of function should be discarded because it is not a good representation of the data. In this example, comparing the squares, you can see that the function selected on the right is a good fit because the red squares are quite small in comparison to the yellow squares obtained with the mean of the data. Here we are simply doing a visual comparison, but the point of using R-squared is that you can quantify how well a function fits the data. This concludes the overview of some of the metrics used to evaluate performance in regression problems. If you enjoyed it and found it useful, please click the like button and subscribe to this channel. Thank you for watching.